sensitivity of aquifer chemistry to changes in carbon dioxide partial pressure, implications for design of groundwater monitoring protocols. So the overall focus of this talk is going to be how we might be able to detect carbon dioxide leakage from a storage reservoir in terms of the overlying monitored aquifer chemistry. And I do just want to take a second to acknowledge the help I got from my co-authors, Charles Hostetler and Julie O'Leary. There we go. So globally, there is a modern push for the geologic sequestration of supercritical carbon dioxide for countering global warming. But overall, the injection of carbon dioxide in the subsurface isn't exactly a new practice. Historically, carbon dioxide gas injection has been utilized for enhanced oil recovery since the early 1970s. While enhanced oil recovery is still a common practice, sequestration has become the bigger focus in research and also in the regulatory world. But nowadays you have to submit a permit application to inject supercritical carbon dioxide via a Class 6 injection well. And you either send that to the US EPA or a state agency that has primacy over Class 6 well applications, which right now is either only North Dakota or Wyoming. And you have to demonstrate that the injection well will not endanger underground sources of drinking water. The regulatory process is also still being optimized. There's only a small handful of Class 6 injection well permits that have been issued and are currently active in the US, but there are many applications that are currently in development, so there is a ton of opportunity for improving the permitting process as we keep moving forward into the future. So the overall technical objective of this talk is to explore how might we be able to detect carbon dioxide leakage from sequestration through the testing and monitoring of groundwater. So a testing and monitoring plan is required during all phases of a geologic sequestration project, and it must be tailored to site-specific considerations. The EPA guidance does recommend monitoring the first permeable unit above a confining layer. So for this group, you have your carbon dioxide storage reservoir, and you have to have a confining layer above that to essentially hold it all in. So what they're recommending is that you monitor that first permeable unit above that you can collect groundwater samples from. So you may also consider monitoring additional units above that and other underground sources of drinking water. And in some cases, that might also be required since you have to protect all underground sources of drinking water from your deep well injection practices. We have to consider how an aquifer might be affected geochemically if carbon dioxide does happen to escape from the storage unit and infiltrate the aquifer. So deep study and understanding of the aquifer's geochemistry, paired with the other site characterization and modeling efforts, will be imperative to developing a cost-effective and limited complexity testing and monitoring program. And that'll range all the way from developing suitable baseline data to choosing appropriate monitoring well construction materials. Okay, so here I would like to introduce our case study. So in Illinois, the Cambrian Mount Simon Sandstone is a deep saline aquifer, which is a major target injection zone for carbon sequestration. On the right is an isopac map showing the thickness of the Mount Simon across Illinois. This unit has been a huge research focus for the Illinois Basin Decatur project, and it hosts the first two successful Class 6 injection wells in the US, which are denoted by the star on the map here. I also noted the location of the Mahomet Valley Aquifer system in this crosshatch pattern on the map, and that is a sole source drinking water aquifer for central and eastern Illinois. So this aquifer system overlies the Mount Simon in some parts of the state that have very similar sequestration potential to this area of the Illinois Basin Decatur project, which indicates that that aquifer may need monitoring if we have future sequestration projects in this part of the state. And I do want to note that the Mahomet is a shallow glacial aquifer, and it is separated from the Mount Simon by literally thousands of feet of stratigraphy and several confining layers. But if we were to install a class 6 well in here somewhere, we would have to drill through that aquifer, and it would be probably a very big point of community pushback. So that will be the point of our case study today. So here's a zoomed in view of our case study in the Mahomet Aquifer. We used hydrochemical data from a paper by Pano et al. In 1994 from the Groundwater Journal. They analyzed 10 samples across the Mahomet Aquifer, shown by the red points on the map. They analyzed for major and minor cations and anions, trace elements, pH and EH. Again, noted by the star is the existing Class 6 wells for the Decatur project, and I noted that to show the proximity of that project in relation to the Mahomet Aquifer. Okay, so jumping into our study design, we are using the Mahomet Aquifer data to see if we can detect carbon dioxide leakage through the geochemical speciation of groundwater. So to do this, we conducted thermodynamic inverse modeling using a program called Visual Mintech 3.1. We entered known system variables for the 10 samples from the Mahomet Aquifer. That includes pH, EH, and the dissolved analytical constituents. And we allowed the program to establish a base case PCO2 value, which is the partial pressure of carbon dioxide. So from there, we simulated the effect of progressively increasing the PCO2 value on the geochemical composition of the groundwater. And as we did this, we examined how the species distribution, the saturation indices of minerals, and equilibrated mass distributions changed as the PCO2 increased by generating Excel outputs and graphs. And before moving on, I do want to mention another thing we did in conjunction with the modeling is a literature review of research that's been done over the past couple of decades on testing and monitoring of groundwater, specifically in relation to CO2 leakage from storage units. And we also reviewed some of the previous successful Class 6 applications to kind of get an idea of what geochemical effects we might expect to see as PCO2 increases and kind of compare our results with previous work. So we could compile a comprehensive list of monitoring program recommendations, which I'll go through at the end of this talk. Okay, so before diving into the results, I wanted to show some examples of the compositions of the Mahomet Aquifer waters. So on the left is a radar chart, which is numerically scaled in moles per liter. So overall, you can see that these are calcium and carbonate dominated waters. There's a bit of a magnesium dominated component as well, and there's some variation to this as well. So we did look at all 10 samples in terms of the effect of increasing PCO2, but for the purposes of this presentation, we're going to look specifically at samples E2 and E8. So for E2, there's more of a sulfate dominated component, and E8 has more of a chloride dominated component. To see if different responses occur, but I do want to mention here that all 10 samples end up giving pretty much the same results in the end. But for comparison purposes and to keep things simple, I'm going to go through these two cases specifically. To set the stage, though, I want to first show how a couple system variables responded to increasing PCO2 for all 10 samples. Okay, so looking at PCO2 versus pH, we can see that as the PCO2 value increases, there is a sharp initial decrease in pH. But after a certain point, that pH decrease levels off. And the way to explain that is that after a certain point, a majority of carbonate is converted to carbonic acid. And you can see by this equation, as you're adding carbon dioxide to the system, you're converting into carbonic acid. And with the ionic strength, as you're changing, or excuse me, increasing your PCO2 value, it's hard to tell by the way this graph is set up, but for all 10 samples, that ionic strength value is not changing as PCO2 is increasing, which indicates a predominance of neutral species. And again, referring back to this equation, as you're adding CO2 to the system, you're generating carbonic acid, which is a neutral species. Okay, so now we're moving into our species distribution results, specifically for samples E2 and E8. Okay, so I want to point out our initial base case values. So note that we have an initial high bicarbonate concentration over 80% in both cases, and we have a low concentration around or below 10% of carbonic acid in both cases. So as we progressively increase our PCO2 value, we are getting a progressive decrease in our bicarbonate and a progressive increase in our carbonic acid in both cases. So this is graphically showing that conversion of carbonate and bicarbonate into carbonic acid. And it's the same case with these other carbonate and bicarbonate compounds. You can't really see it on the graph because the concentrations are so small here. I do want to note here that no other major or minor cations and anion concentrations were notably affected by the increases in PCO2. Okay, so moving on to trace elements. So we're looking here specifically at arsenic. Okay, so for samples E2 and E8, again, looking at the base case, we have an initial high concentration of hydrogen arsenate in both cases, an initial low concentration of dihydrogen arsenate. And as we progressively increase that PCO2 value, we get a decrease in the hydrogen arsenate and an increase in dihydrogen arsenate in both cases. And we also get a increase in arsenic acid, which you can't see because the concentrations are so small. So again, graphically, this is showing the conversion of hydrogen arsenate into dihydrogen arsenate and also into arsenic acid in very small concentrations. So I do want to note that no other trace elements appeared to be notably affected by the increases in PCO2. However, our data source did only analyze a small selection of trace elements. We would expect other strongly complexing anions like arsenic, such as chromium or cobalt, to behave similarly to this. Okay, so moving on to saturation indices. We did also look at saturation indices for different mineral groups, including the silicates, sulfates, and carbonates. So I don't show them here, but the silicates and sulfates were unaffected by the increases in PCO2. And as we would expect from what we saw with the species distribution for carbonates, the carbonate mineral saturation indices do decrease with increasing PCO2. So the saturation index is a logarithmic scale, and I want to point out where the 0 point is for these. So anything above 0 would tend to precipitate out of solution, and anything below 0 would tend to dissolve. So what this is showing is as we are increasing our PCO2 progressively, we would tend to dissolve those carbonate minerals into solution, and that decrease is logarithmic as you increase that PCO2 value. So what this is suggesting is that you're having an increasing potential to dissolve any carbonate in the aquifer solids and potentially alter the framework of the aquifer pore space. Okay, so just a quick summary of my case study results. So as the PCO2 increases, we did see the groundwater become more acidic, especially initially. The carbonate and bicarbonate were converted into carbonic acid. Hydrogen arsenate was converted into dihydrogen arsenate and additionally into arsenic acid. And the silicate and sulfate saturation indices were unaffected, while the carbonate saturation indices strongly decreased logarithmically. And again, I wanted to note that this was the case for all 10 samples that we looked at. Okay, so why do we want to do experiments like this? And why do we want to look at the geochemistry? So I want to dive into some recommendations for the monitoring program based on our case study, but also in conjunction with the thermodynamic modeling, like I mentioned earlier. We also conducted a thorough literature review of research that's been done over the past couple decades on the testing and monitoring of groundwater, specifically in relation to the CO2 leakage from storage units, as well as a review of previous successful Class 6 applications. And we did use both as the basis for this list of recommendations for developing a monitoring program that's both robust and cost effective. So these first few recommendations on this slide mainly go hand in hand with EPA's regulatory guidance. So first and foremost, a monitoring program should be constructed based on the outcome of site-specific geochemical and flow and transport modeling. Your modeling results will give you an idea of how the intrusion of carbon dioxide and saline waters from the injection zone might affect your groundwater quality in your monitored unit and over what time scales, as well as how you should optimally design your monitoring well network in terms of your well construction details, your well spacing, how close to your injection well to put your monitoring wells, etc. Secondly, as more site-specific data are obtained through the operational phase of injection, your models should be updated with these new data and the predictions should be re-examined. And this may mean, more often than not, making amendments to your testing and monitoring program to ensure that it remains effective and protective of the underground sources of drinking water. Another thing to consider is that alternative methods, and that includes the analysis of isotopes, dissolved trace gases. Those can be considered, especially when the monitored unit is low in total dissolved solids or salinity. And it is important to consider these additional methods that will be sensitive enough to pick up whether a potential geochemical issue is actually related to CO2 leakage or if it's just natural variability in your monitored unit. And from looking at the previous Class 6 applications, I've seen that it's pretty common to do these analyses in conjunction with traditional geochemical analyses. Whereas if you're thinking of something like a CCR monitoring program or landfill monitoring program, you wouldn't really see something like this, and you wouldn't really have to consider it. Okay, so this last point is more geared towards the case study results and the geochemistry of the aquifer itself. So in general, for relatively dilute aquifers like the Muhammad Aquifer system, changes in pH, total dissolved carbonate, and strong complexing anions will be the strongest geochemical indicators of initial CO2 leakage. However, even small variations in composition could lead to false positives or exceedances in the monitoring network. So with that, it's absolutely key to establish representative baseline in order for your monitoring program to be both robust and cost effective. And we know this from working at CCR sites and landfills. Using an insufficient amount of background data is not going to account for seasonal variability. In addition, it's also important to optimize your monitoring parameter list to maximize your statistical power in your monitoring network. If you're trying to look at too many parameters, it's going to be a lot more likely to have false positives during a given monitoring event. And going back to the main point, narrowing your list down to what you really expect the strongest geochemical indicators of leakage to be based on your monitoring efforts, and leaving off any parameters that won't be affected or aren't relevant will be to your advantage. Okay, and that's all I have, and I would be very happy to take any questions anybody has. So thank you for your time.